Thank you, Nick, for the nice introduction, and welcome. Good morning, everybody from Edinburgh. So we've got a tight schedule, so I'm going to try and compress this as much as possible. I should say, as Nick said, I am a computational scientist with interest in manufacturing, among other things. And some of the stuff that we'll talk about today have stemmed from discussions that I had over the last year with Roger Woods at Queen's Belfast. Now, before I go into the detail, I want to say something about my title. So most of you will probably recognize that diagnostics and predictions are computational tasks that become increasingly complex when you have very large models, lots of data, or you want to compute something in 0 time or next to 0 time. So this can be invariably very, very simple if you do it on a toy scale, but if you do it on a big scale, they can become complex. So for today, this is my mode, right? So I'm going to do large-scale computing on the fly. Not only that, I want to do it at the edge of the process, of a manufacturing process, for example, using some light hardware, right? Without using a high-performance computer. So let me see if I can flip the slide. No? Right, okay. So one of the possible frameworks to accommodate this task is what we call randomized algorithms, also known as sketching, which is a way of doing scientific computing when we have limited resources or strong time and communication constraints. So what kind of scientific computing are we talking about? I think for the context of this application, I would think probably one of 2 things, either process modeling, where one has to simulate the process to be able to predict some outcomes, or you have to solve an inverse problem where you will use some data from your true process to be able to estimate its parameters, and that's probably going to tell you something about either the process itself or the product it develops. Another thing to mention, that in case you do this, because you're going to compute an estimator, you may also want to do some uncertainty quantification, because you want to have a feeling of how loose that estimator is. And if it's too loose, then you shouldn't be taking that much, you shouldn't be putting too much trust on it anyway. Right, I should briefly mention that this randomized algorithms is now emerging as a research area in its own merit. And we had our first workshop organized by some of the main funding agencies in the US late last year at the beginning of this year. It was quite well attended. So I'm going to extract I'm going to give a brief description of what this is about without any mathematics, of course, we haven't got the time. And I'll talk about 2 problems in responsive manufacturing, or in manufacturing, if you like, that this could find application to. Okay, so here's my abstraction of a process, not just a manufacturing process, but project. You have some kind of sensorized equipment that extracts data. You push them through some sort of processing box. You can forget what is inside at the moment. So once you get this data, you may do some diagnostics, which, as I said before, it kind of involves solving an inverse problem. Or you may assume that this thing is now describing a stage inside a multi-stage manufacturing process. And you may want to use the data there to be able to predict what the product is going to be like at the end of the next stage, or at the end of the whole process. And this is kind of what the predictive analytics means. So one looks at the back, going in the inverse way, and one looks forward, looking at the future. Now, all this is nice and good, of course, always in abstraction, but things start to go wrong when the data that you're pushing into the system is high dimensional. And what do I mean by high dimensional data? Well, essentially, I mean anything that involves imagery, some high definition images or video, or even some high speed time series data. If they get pushed into the system, then you need to somehow beef the computational power up. Right? You need to squeeze more resources into the system, which isn't always the most practical thing to do, or the most cost-effective thing to do. So we looked at the alternative, right? So let's just get rid of the electronics and the algorithms, and let's put a human inside. Let's see how that would cope. Let's put an operator who knows what's going on. It has the experience, it's seen this thing before, but it gets overwhelmed with data. So how would that person react? He needs to analyze the data that come in front of them and make a decision quickly. Obviously, because of the time constraints, we cannot fully analyze the data. So that person will go, if you like, by his intuition or his experience, his instinct to pick some of the data that they feel they trust them more, and then they make a decision based only on that subset of low-dimensional data. And this is exactly the thing we want to replicate with what we call the combination of sketching and transposition. So sketching will look at the data, but they will not touch, it will pick only a small subset of that data to process. And once that's done, then the transposition processing will process this data at variable precision, because those calculations need not be done very accurately. Okay, so I guess the question to be asked here is whether this sort of diagnostics and predictions that we do in this way, by just looking at partially at the data, can be done, would they be different from what we would have got with the whole data set? And of course, the answer, you know, is going to be yes, but I also would like to give you some further evidence to convince you, if I may. Now, if you look how this system, these monitoring systems are designed, and that kind of is, in a way, it's been reflected by the previous talks. They are kind of modular optimized. So you have the sensing, the comms, processing, whatever. And these are units that are optimized per se, individually. So those who develop the sensing would not interfere with what kind of algorithm will be coming into processing those data and so on. And this is kind of an overkill, right? Meaning that this thing is just too good for its own good. Meaning it's just, you end up with having too many data, making it too slow and too expensive. If we look at this end-to-end optimization, we can make allowances for some of these stages to be done coarsely without losing too much. We're going to lose something, that is for sure, but we can minimize what we can lose. And of course, we can gain speed and efficiency. So we say that, you know, if, for example, if the decision envelope is limited, then maybe we don't have to wait until the algorithms converge to their minimum value, or maybe we can allow a higher error, and therefore maybe we don't need the cloud. We can do some rough and dirty calculation at the site, and maybe we don't need to sample at subliquid for that thing to happen. So in this interconnection that we look for in between these stages, which prompts into this paradigm of task-specific sensing and processing. So as it is now, it can do a number of things, and that's expensive. We're trying to reduce the scope and make it more flexible. Okay, so let's see what kind of complexity can we afford realistically to do in real time. So we can do simple detection and statistics, things like seeing whether my signal is within some admissible range, or get some rolling averages. This I can do, right? Even if they're high dimensional, you don't need to worry about stuff. But things like online regression or model learning, these are complex with high dimensional data. So the concept of data and model sketching is to trade a small percentage of accuracy for a manifold speed improvement. And in the case of model learning, for a manifold memory saving improvement. So how does it happen? Again, I'm not going to give you the detail, but overall, data sketching uses some criteria, which we call statistical or physics-based leverage scores, to prioritize which data are the most informative. Now you might be thinking, but how does it know before processing the data if the data are informative? So there is a way to do it, and this is reminiscent to the intuition of somebody who looks for which data are going to be the more informative. In the case that I've talked about before, sometimes you know the physics that correspond to the data, and that can drive you. Sometimes you have statistics. But at the end of the day, we extract a small subset of the data to play with or do computations with. And therefore, all the conventional calculations that go into these tasks become estimators. And that means that if you were to repeat them, every time you get a slightly different answer, which is a bit weird, but this is the kind of compromise that we did by allowing a small percentage of accuracy. And somebody will ask me later on, I'm sure, what's small enough in this case. I would say something 5% relative error or less. Yeah. Okay, so there is Still a lot to do in this stuff, but the general take-home message is that with high probability, you can go through a massive data set and get it processed quickly, simply because there's no magic essentially involved. You just process a small amount of data. And you see I've sort of highlighted the high probability because this thing at some point will fail, but you can control how much, when it will fail. And again, in this, what we're trying to do when we design the implementation of these methods is that they will not fail, they will fail at least once on every 100 million or even more runs. So that's kind of a risk that it's unavoidable. Now, quickly, to take advantage of all these things, obviously you need computing platforms that are suitable for processing sparse data structures efficiently, right? Because you have these massive matrices and vectors. If you only pick a small percentage of the data, you don't want to be carrying the zeros with you. And here I've got a list of some ready-made software that's based on these technologies, and it's been used a lot. I also want to probe your attention to this small enterprise, Lydon, out of Paris, that now actually manufactures processors that use light scattering inside the chip to emulate this random picking on inside their, this random sketching inside their processors. Okay, the two manufacturing applications, very briefly, I am involved with this. The first one is image-based metrology for quality assurance. This has been a problem that has been suggested from a company in the semiconductor manufacturing business. They manufacture silicon wafers, or they go under some high definition microscopes, and then they inspect them to see if they have the right dimensions. So obviously you get these huge high resolution images. They go through computer vision algorithms that do the business. You know, they measure them, they find their features, and if they're good enough, they let them go, otherwise they do something else. All this good, but if there is a loss of focusing by these instruments, then the whole process collapses. So what we need to do, what they want to do, is build in an online image restoration that will deblur and clear this image before metrology kicks in. The second area is something that to somebody would be something like a digital twin of a process. So when it refers to this closed loop control in power bed fusion, where they use high intensity lasers to sinter powder into solids. And while they do this, they extract temperature data from the surface, and that data gets fed into a digital model that would profile what happens inside the part as it gets printed out. And they want to see whether they are overheating or underheating so that they can adjust the intensity of the beam or reroute it in some way, because if they don't, there is a chance that the part, after it gets manufactured, it will have some structural faults. So again, the computational issue here is to sketch the heat transfer as it happens inside the 3D printer using some numerical solver like the ones we use in engineering. Okay, so I will, in the interest of time, I will leave it here with the final message that you can find a lot of more information about this in the internet. Unfortunately, the area itself comes with different names as many other areas in our times. There is still a lot of analysis to be done. It's still in the research level to understand when it fails and how often it fails. It has some advantages over the neural networks that I'm sure some of you are familiar with. And with that, I would like to thank you and also thank our sponsors for this project that they funded a few years back, and they gave us an opportunity to present the stuff for today. Thank you very much.